So last week we started chapter 5. We kind of spent all week on section 5.1, which kind of gave us the theory of some of these things. So last week we were looking at diffie q's that look like this: y double prime plus p of xy prime plus q of xy equal f of x. This is what we started with. And these are second order linear differential equations. And then we focused in on equations that look like this: y double prime plus p of xy prime plus q of xy equals 0, which are second order linear. And since we've got it equal to 0, these are homogeneous differential equations. Okay? And the big takeaway is that if it's a second order equation, we're thinking in the back of our minds there's two integrations that are going to happen to get us back to the original function. Each of those are going to spit out an arbitrary constant. So what we're looking for our general solution is a c1 y1 plus a c2 y2, where the y1 and the y2 are solutions that are different enough to be able to capture the general solution of the differential equation. Different enough, y1, y2, different enough means that they're linearly independent, meaning that if you look at their Vronsky, it's never 0. Okay, and this came from Cramer's rule. So that's kind of what we did last week. We had an existence and uniqueness theorem that if we tacked on initial conditions to such a thing, as long as the P and the Q were continuous, and we had some initial conditions. I think we called them K's for some reason. I don't know why the book changed up. K naught and K1. We tacked on initial conditions. As long as our P and the Q were continuous in an open interval about x naught, we were guaranteed not only a solution, but only one solution. So that's kind of where we spent our time last week, is the theory of these equations. This week, we're going to actually talk about how we start solving these equations. And so we're going to look at a special case of these equations called constant coefficient. Second order homogeneous differential equation. So constant coefficient means what you think. If you think of these as coefficient functions, a constant coefficient diffie q is going to look like a2 y double prime plus a1 y prime plus a naught y equals 0, where a naught, a1, a2 are real numbers. And to make sure we have a second order equation, we're going to specify that a2 isn't 0. And notice if a2 isn't 0, we can go ahead and divide through by a2, and we can put it into the form y double prime plus a1 over a2 y prime plus a naught over a2 y equals 0, which is in the form of the linear equations we had last week. So here would be our p of x function, here would be our q of x function. And since these are constant functions, they're continuous everywhere. So everything that we talked about last week applies to this specific case. And so we're going to talk today, and probably today and tomorrow, about how to solve these equations. So how do we solve constant coefficient equations? And I know that the high schools are closed, so Zoran's not here. Zoran, this method will generalize to any order you want. I can just anticipate you thinking of that question. But yeah, it'll generalize to any order you want. So here's what we're going to do. Here's what we're going to make this assumption, which years ago I used this word. This is the German word Ansatz for assumption. And for whatever reason, the mentor students just glommed onto that. They love the word Ansatz. Okay, so this is the assumption we're going to make. So if we think about what kinds of functions are going to behave this way, you're basically taking a function and its derivatives, and you're taking a linear combination of a function and its derivatives and getting 0. So as you take derivatives, the function really isn't changing much. The coefficients might change out front, but the function itself really isn't changing much. And so that's, if we think about it, if we think about the ones, we could try exponential functions. So we're going to make this assumption that my solution looks like e to the mx. Because when I take derivatives of e to the mx, the m just comes out front. So every time you take a derivative, you're just multiplying by m. And so what we can do is we can stuff this into the differential equation. So a2y double prime plus a1y1 y prime plus a naught y is 0. And we're going to stuff in y equals e to the mx. And so we would get a2 y double prime. You've taken the derivative twice, so there's 2 factors of m, plus a1 m e to the mx plus a naught e to the mx is 0. And now if you notice, I've got a common factor of e to the mx I can factor out. So I'd have an a2 m squared plus an a1m plus a naught e to the mx equals 0. And something we've talked about again and again in this class is this nice property. E to the mx is always a positive number. So it's never 0. So I can divide both sides by e to the mx and not worry about losing any solutions. That means that this polynomial here in m has to be 0. So a2m squared plus a1m plus a naught has to be 0. This is called the ancillary equation or the auxiliary equation, depending on what book you're using. Basically, we took a second order differential equation and turned it into a second degree algebraic equation. Okay. So let's do a quick review on quadratic equations and how they work, and that'll set the stage for the sorts of things we'll get into here in the next day or so. So if you're trying to solve quadratic equations, one thing that helps you figure out what's going on is the discriminant. The discriminant is what discriminates what type of solutions we can expect. The discriminant is it's the b squared minus 4ac. So in this particular case, it would be the a1 squared minus 4 a2 a naught. The discriminant is what lies underneath the square root in the quadratic formula. And so if what we have under here, we'll call that D. So if D is bigger than 0, if the discriminant is bigger than 0, then we get 2 unequal real solutions. because we got a real number plus or minus another real number, non-zero real number. If d equals 0, we get 2, and I'll put that in quotes, we get 2 equal solutions. This is the concept of multiplicity. You might or might not remember that. So we get a repeated real solution. And if d is less than 0, we get 2 unequal non-real solutions. All right, because we would get a negative under there, and that negative under the square root would fly out, hit you right in the eye. Okay. So as we go through in each of these cases, we're going to have to think about what that means in terms of what our solutions look like. Okay. So that's kind of the buildup of what we're doing here in section 5.2. First thing we want to do is to prove that if we have, say this first case, we have 2 unequal real solutions, we have 2 different m's, then that we are linearly independent. Okay, so we can do that using the Vronsky. So if I look at the Vronsky of e to the m1x, e to the m2x, if we want to show linear independence, if m1 is not m2, we need to show that the Vronsky isn't 0. Okay, that's how we can show linear independence of these functions. Let's go ahead and do that. Remember how we calculate the Vronsky from last week. You put the functions in the first row and their derivatives in the second row. Now we do the zig minus the zag. I can rearrange these factors. I'm going to have the m2 factor. I'm going to pull that out front. And then once again, we've got exponentials with the same base. So since these exponentials are both base e, when I multiply them together, I can add the exponents. And now I can factor this exponential out from both of these terms. I'll be left with an m2 minus m1 e to the m1x plus m2x. And once again, we go back to this property of exponentials. E to any power is positive, so that's certainly not 0. If m1 is not equal to m2, then m2 minus m1 is not 0. And so we can conclude the Vronsky isn't 0, which proves that those two functions are linearly independent. Are there any questions on the Vronsky setup here? Or the conclusion then we can draw from the Vronsky? So that was one of the properties of the Vronsky we talked about last week. If the Vronsky is not 0, then the functions are linearly independent. But as you'll see here in the next week or two, there are examples of functions which are linearly independent, and yet the Vronsky still zeroes out. So I think it was on a worksheet last week, and it comes back on a take-home or a test or something here in the near future. Okay. So let's solve the following differential equations. So here we go. So now we're actually solving some of these second order equations. And remember the assumption, the ansatz, if you will, for each of these is that y equals e to the mx. All right? And so we can go from the differential equation into the auxiliary or ancillary equation. Every time you take a derivative of e to the mx, you're going to spit out a factor of m. So 2y double prime is going to have 2m squared. Minus 5y prime will give you 5m. Minus 3y is 3. And you'll have a factor of e to the mx, as we saw earlier. There'll be a factor of e to the mx that we can just factor out and cancel out. Boom. Here we go. Now we're down to a quadratic equation. Now, you can solve quadratic equations every single time using the quadratic formula, but we try to avoid it if possible. Let's see if things factor. So we can try to factor this. So let's see if, looks like Tim has tuned in here. See if Tim is willing to volunteer a factorization of this. Looks good. 2m plus 1 times m minus 3. Perfect. Remember, we always factor against 0 because we have a property of real numbers. If you have two real numbers that multiply to give you 0, the only way that's going to happen is if one or the other is 0. So now we can split the factors here. 2m plus 1 is 0, or m minus 3 is 0. So here we get an m equal minus a half. Here we get an m equals 3. And remember, these are the coefficients of x in the exponential. We have two different exponential functions. We've got an e to the minus 1/2 x, e to the 3x. We know that these are linearly independent. We know from last week all we need are two linearly independent solutions to form the general solution. So boom, that's the general solution. C1 e to the minus 1/2 x plus C2 e to the 3x. We're done. We've solved the diff EQ. That's the general solution. So we're taking a differential equation and turning it into an algebra equation. And this isn't the last time this will happen. This will also happen in chapter 8. All right. Any questions on the methodology here? Let's move on here. The next example. Once again, we have a constant coefficient differential equation. We're going to make the assumption, the ansatz, y equal e to the mx. Y double prime would be m squared. 2y prime would 2m. 1y would be 1. Quadratic equation, m squared minus 2m minus 1 is 0. You might try to factor this nicely. It doesn't factor nicely, so we can always bust out the quadratic formula here. The first thing I always check with quadratic formula is the discriminant. What kind of answers are we going to get? So what's that discriminant work out to be when it's all said and done? Positive 8, good. Since that discriminant is bigger than 0, I know I'm guaranteed two different real number solutions. And as long as those numbers are different, I know the corresponding exponentials are linearly independent. So I just have to figure out what the m's are, and then I'm pretty much done. So m is the opposite of b. plus or minus the square root of the discriminant over 2a. The opposite of negative 2 is positive 2. You can simplify the square root of 8. Let's actually go through the... I've seen too many mistakes with this. Let's just take this one step at a time. All right, let's actually go through this one step at a time. The negative of the negative, the opposite of the negative is a positive 2, plus or minus. Now let's talk about how you correctly simplify radicals. Radicals are powers. They're the 1/2 power. They work well with multiplication and division. They don't work well with anything else. So if I'm going to simplify this, I need to write it as a product with perfect squares. I can factor 8 down into a 4 times a 2. And now we need to correctly simplify this. Very common mistake is these 2's cancel, and you're left with plus or minus 2 root 2. There's all kinds of incorrect answers that can come from this, but we've got a division and we've got a plus or minus. So if you need to, you can think of this as 1/2 times 2 plus or minus 2 root 2 to help remind you that you do distribute. And once again, the reason I'm taking the time is I've seen these sorts of errors, and these sorts of arithmetic and algebra errors will derail you greatly if you go through these problems. So you just distribute it through, or think 2 over 2 is 1 plus or minus 2 root 2 over 2 is root 2. There's our m's. So we have 2 different solutions. That means that the corresponding exponential functions, remember we're looking at y equal e to the mx's here, they are linearly independent, and so I can confidently write my answer as a c1 e to the 1 minus root 2 x plus c2 e to the 1 plus root 2 x. There it is. Okay. Any questions on that example? Getting the roots m, getting those solutions, simplifying them. If you try to rush through the algebra, you'll pay for it later. So just take it one step at a time. The next example showcases something that we're going to see a little bit of later on, if not today, probably tomorrow. Solve the differential equation y double prime equal k squared y, assuming k is a positive constant. So this gives us a parameter here. Now, if this looks familiar, it should. I think this was on like your first take home. I had you verify solutions, so you can go back and look on that. So I got the y double prime is k squared y. So once again, we're going to make the ansatz here that y equals e to the mx. Substitute that in. The second derivative, every time you take a derivative, you're going to spit out a factor of m. So we got an m squared there. There is no first derivative. There's just the function itself. So m squared is k squared. We could subtract things over and factor, or we could just extract square roots here. So m is plus or minus the square root of k squared, which is plus or minus the absolute value of k. But we're told to assume k is a positive number, so we don't need those square roots, or the absolute values rather. It's plus or minus k. Now, since k is positive, k and the opposite of k are going to be two different numbers. Like, for example, if k were 2, we'd be getting plus 2 and minus 2. or plus a half minus a half, plus 10 minus 10. So since k is positive and not 0, we're getting two distinct answers here. And so one way to write that solution, once again, we could confidently write, whoops, looks like I adjusted that knob there. Let's try this again. I can confidently write y equals c1 e to the minus kx plus c2 e to the kx. That would be one way to write the solution. But you may remember back to calculus, or you may remember back to take home 1, that e to the kx, e to the minus kx, there are some combinations of those that are sort of more convenient to use depending on what sort of discipline you're in. So recall, the hyperbolic cosine of kx is e to the kx plus e to the minus kx over 2. And the hyperbolic sine of kx is e to the kx minus e to the minus kx over 2. So what you can do is, if you look at the solution we've got, it's linear combinations of e to the kx and e to the minus kx. You can actually solve these equations for e to the kx and e to the minus kx. And you can rewrite a linear combination of these functions as linear combinations of cosh and sinh. Okay. So for example, whoops, let's call it C3 cosh kx plus C4 sinh kx. I could write that as C3 e to the kx plus e to the minus kx over 2 plus C4 e to the kx minus e to the minus kx over 2. And notice what I've got here is a linear combination. If I look at e to the kx, I've got a C3 plus C4 over 2 e to the kx plus, and if I look at an e to the minus kx, I've got a C3 minus C4 over 2. And I could just relabel this as a C1 and relabel this as a C2. So arbitrary linear combinations of cosh and sinh are going to get us back to arbitrary linear combinations of e to the kx and e to the minus kx and vice versa. Okay, so you can convert between the two solutions. All right. So oftentimes that's what you'll see. For this equation, y double prime equals k squared y, or you might see it y double prime minus k squared y equals 0, depending on the physical application you're looking at. So when you see this, yeah, you could do that, but you can turn cinches and coshes. I guess here we're putting sinh first, and then cosh for second. Does that make sense or not, folks? See what's happening there? We're just looking at linear combinations within linear combinations. And we will come back and see this again tomorrow with the regular circular functions, or the regular trig functions, the circular functions, sine and cosine. All right. As far as quizzes and tests go, either one is fine for me. All right, I just want you to be aware that this is a thing. Okay, here's an example. What happens when you try to solve this equation? This is always good, right? We had a couple of these in calculus, Calc 3. We try to do something breaks down. Let's see what happens here. All right, once again, we recognize it as a constant coefficient homogeneous differential equation. Constant coefficient means all the coefficients of y and its derivatives are constant. Homogeneous means we've got all the y's on one side equal to 0. So we're going to make the assumption, the ansatz, that y equals e to the mx. What's the auxiliary equation or ancillary equation going to be? What's the equation in m's we have to solve for this one? Yep, m squared minus 6m plus 9. Very good. All right, so once again, we can try to factor it. If it doesn't factor nicely, we could hit it with quadratic formula. But how does this one factor? Yep, m minus 3 squared. So this is an example of where the discriminant is 0. And so we get only one solution, m equals 3, which means we only get one factor, y equals e to the 3x. Okay. So in order to figure out a second linearly independent solution, it has to be close to e to the 3x for this to work, but it has to be different enough. So we're going to make use of a technique called reduction of order. And we'll talk more about reduction of order I think the week before spring break. So not next week, but the week after. Here's reduction of order. Reduction of order says, okay, we've got a second order differential equation. Suppose we've got one non-trivial solution. So what we're going to try to do is we're going to find another function, u, so that if I multiply y1 by u, we'll get another solution. In other words, we're gonna stuff this into the diffie-q. Knowing that y1 is a solution. So y1 double prime minus 6y1 prime minus 9y1 equals 0. And the hope is that since I know part of this differential equation, I'll somehow be able to reduce the order and turn this second order equation somehow into a first order equation. Okay, so here's what we're going to stuff this in there and see what happens. So every time we take the derivative here, I'm going to have to use what rule? The product rule. Okay, so we're not going to do the generic one today. We'll do that. So this would be u times e to the 3x. So let's start stuffing this in. So y prime would be derivative of the first factor times the second plus the first times the derivative of the second. Now, anytime we take the derivative of e to the 3x, we're going to spit out a factor of 3. And then y double prime, product rule again. Derivative of the first factor times the second plus the first times derivative of the second. The second factor is going to spit out a factor of 3 plus Now we're moving to the derivative of the second term here. Derivative of the first factor there, plus the first times derivative of the second. Another factor of 3 spits out. And so we can do a little simplification here to get that. And once again, the hope is if we stuff this into the differential equation, enough stuff will cancel out that we'll essentially get a first order equation. You know, we're looking for two pieces. We have one piece. Can we use that one piece to get a second piece? All right. Right? Because we know, I guess, we know that if this is a constant, this will work. So we're just, instead of assuming this is a constant, right, we're assuming it's a variable. So that's kind of what reduction of order is. It's like, okay, well, maybe we know constants will work, but we need something that's not a constant. So we're going to make that a variable instead. That's kind of the reasoning behind it. So let's go ahead and stuff that in. Y double prime minus 6y prime plus 9 equals 0. Let's stuff this in. I got u double prime e to the 3x plus 6u prime e to the 3x plus 9u e to the 3x minus 6 times y prime u prime e to the 3x plus 3u e to the 3x plus 9y u e to the 3x. And that's, we want that to be 0. And by golly, look what happens. We got the u double prime e to the 3x. But look what happens to the 6u prime e to the 3x. Right? That's going to cancel out. We've got 9u e to the 3x plus another 9u e to the 3x. That would be an 18u e to the 3x. And by golly, look what happens. That all cancels out. So now we're left with that equal to 0. And we know that e to the 3x can be all kinds of different things, but that's never 0. So really, I'm just left with u double prime equals 0. Now, as we'll see in the general reduction of order, what will happen is you'll be left with a u double prime and a u prime, which is a way to reduce it down in some sense to a first order equation. And we'll talk more about that in a couple weeks. But this one we can solve pretty quick by just doing our integration. In fact, this was the first, when we talked about second order equations, we did just this. You're going to get u equals a C1 from the first integration, and then a C2x. There's your linear equation. Okay. So if I look at y equals u e to the 3x, that's C1 plus C2x e to the 3x. I'm getting a C1 e to the 3x, which is what we had going into this. But notice I get a C2x e to the 3x. So notice it's not a constant multiple of e to the 3x, but it is a variable multiple of e to the 3x. And you can check in the privacy of your own home, if you plug this in to y double prime minus 6y prime plus 9y, you will in fact get 0. Right? So I would encourage you to do that. To see how the product rule works in this specific case, to zero stuff out. Really, all you really have to do is go back to this equation here, because this is the generic one. All you have to do is go back to here, and with the notion that u equals x. So if u equals x, u double prime would be 0, u prime would be 1. You just fill that in and show that you get 0. So there's really not much to do there, but it does work. Okay, it is a solution. The question is it linearly independent, right? Is this different enough? And how do we check for linear independence? If you got two functions, so is the set e to the 3x, x e to the 3x linearly independent? How do we check for that? Yeah, the Vronsky. So here we go. It's actually Polish. I think Vronsky was Polish. I could be wrong about that, but so let's take the Vronsky. So I put the functions in as is, the first row, and then their derivatives. So the derivative of e to the 3x is 3e to the 3x. And once again, to take the derivative of x e to the 3x, what rule do we have to use? Product. Derivative of the first times the second, plus the first times derivative of the second. And now we do the Eric's zig minus zag. So once again, when you multiply with the same base, add exponents. So e to the 3x times e to the 3x is e to the 6x plus 3 e to the 6x oops, I'm sorry, there's an x in here. I forgot this x plus 3x. Minus 3x e to the 6x. Sure enough, those cancel out. I'm left with e to the 6x. And e to the 6x can be lots of different things, but it is never what? 0, which verifies linear independence. Okay. You can redo this last example. You can redo this last example, but everywhere you see a 3, you could put in a generic m. And so if you get a value of m and you get it twice, then that's going to be your solution. All right? So you can think about that. A lot of these proofs in DiffyQ, a lot of these derivations are very computational in nature, which is nice because it's just, we're sort of at that sophomore level between just, schlepping letters and numbers around. We're now kind of saying, okay, well, let's use some generic things. And hopefully you've seen that throughout the homework here in Calc 3 and in DiffyQ. If you had me for Calc 1 and Calc 2, you've seen that as well. But we start to introduce these parameters to prove things in general. Okay. So I'll leave this for you to do. This is the Vronskian of those. The same thing is going to happen once again. Instead of having a 3 in here, it's going to be an M. So you can trace that through. Nothing's going to change. Okay, so here's the theorem. All right. So for this last example here, we only got a couple minutes. We got started a couple minutes late. We were waiting for people to tune in. Let's just go through the highlights of this, and then I'll let you fill in the initial values here. But we've got y double prime plus 25y equals 10y prime. And sure enough, when you set this against 0, when you set this equal to 0, how does this factor? Yep, you get m minus 5 twice. Okay, so remember the assumption here was a y equal e to the mx. So what's my general solution going to be? We're going to have a c1 e to the 5x plus, well, we got 5 twice. All right, so we're going to slap on a factor of x. Like that. So one of my students last year before, there's this, it's called Flex Seal. I don't know if you're familiar with this Flex Seal. It's like a tape. And there's an infomercial where you've got this guy, you've got water leaking, and you just slap the Flex Seal on, it stops the leak. So it was like 1 or 2 years ago, a student said, slapping on this factor of x reminds you of Flex Seal. You've got this problem with the diff EQ, you got repeated root. How do you fix it? You just slap on a factor of x. Okay? I thought that was kind of funny. Anyhow, at this point, you would impose the initial conditions. So you'd have y at 0 would be -2. Then you'd have to find y prime of x and then look at y prime at 0 being +2. Once again, it's an initial value problem because you have the same x value for both the function and the derivative. This specifies a point. This specifies a slope. That'll help you find your C1 and C2. In fact, y at 0 is -2. That's going to drop out. You're going to get your C1 right away. I'll leave those details to you. All right, so that would be your final answer. Okay. All right, tomorrow we're going to get to look at what happens if you get non-real solutions to that quadratic equation. We're going to get to bust out Euler's formula, and we're going to look at Euler's formula, sine and cosine being linear combinations of complex exponentials. So that should be fun. Make sure you tune in for that. Thanks for tuning in, folks. Got a couple people showed up today on President's Day. Appreciate that. Have a great rest of your day. Enjoy the sunshine. We'll see you back here tomorrow.